Hi. So listen, I have your new data set. I chosen this one, but you can do the same thing for any other. Okay, and we do the we go through the same steps. So you load the package, you load the second package, and then you load the data. After loading the data, of course, you build up a model over here, right? And now look, burn-ins and iterations basically, look, when you have so many regressors, the model space becomes very, very large. With 48 regressors, there are billions of models. So we use this Markov chain Monte Carlo model composition algorithm to get basically the information about the entire model space from the sample of best models. And now look, burn-ins are the number of models we disregard at the beginning when we do the sampling, and iterations is how many models we are actually using. And look, what you need to, I already did this for this data set, and those are the results I've obtained. Okay, look, when you do it, basically you need to make sure that here correlation PMP, this is the correlation coefficient between uh, posterior model probabilities obtained from uh, models calculated analytically and from the models that have been approximated is above 0.99. If it's above 0.99, it means that the draws we've done are working perfectly fine, as it is in this case. So you don't need to do more iterations. You can actually, if you will have a problem with other data set, all you have to do is to increase these numbers. Here you have 2 e plus 0.4, which translates, as you can see over here, to 20,000. Here you have 4e plus 0.5, which translates to 4 times 100,000, 400,000. And as you see, it was enough to get a good result. Now, a little bit about the interpretations. Look, I will send you a text where you have this put up in a really nice way, condense the entire information. But let me just explain. Look, here we are not unlike in the case of classical statistics. We use this PIP, posterior inclusion probability. Look, generally, we can start looking at variables when this PIP is bigger than 0.5, which means that posterior inclusion probability is bigger than prior inclusion probability. But you already written about it in your methodology, so I assume that you will know what it is. Okay, so look, here we can start with those models, and we see that here the models are getting better. I'm sorry, variables are getting better, so we can be more sure that they should be in the model. And look, here we have variables with very high posterior inclusion probability, which means that the data suggests that those variables definitely should be in the model. Now, how do you interpret the data, the results? Look, again, you have posterior mean. Posterior mean is like a coefficient in a regular regression, and posterior standard deviation is like a standard error. Of course, these are a little bit broader concepts, but it has no influence on the results. Okay, look, what we are going to do now is that I'm going to copy those results to Excel. We can copy it all, but for now we're going to just use this one. Okay, and I'm going to open Excel, and then I'm pasting it. Right, now the good thing is to change dots into commas. I already did change everything. Okay, and now look, you go to data, I'm sorry, I have Polish Excel. Then you go columns as text as columns, and here you will have like constant space or tabs, something like this. You just go next, next, end. And as you see, now it turned into a very nice table that you can easily then put in your thesis. This part we don't need, so we can just delete it. The rest, let's treat it as numbers. And let's use like 3 zeros after the comma. Okay, so look, those results that you've got over here, you can put on them interpretations exactly the ones like those you have in regular regression. But it also gives you another thing you can do. Because look, if we want to find t statistic, basically we take posterior mean, so coefficient, we divide it by its standard error. And look, here you get another criterion. Also, it will be described in the text. If the absolute value of this ratio is bigger than 2, like here, -5, but remember, absolute value, it means like it's a corresponding to be statistically significant at 99% level in regular classical statistics. If it's above 1.3, it's like 90%. If it's above 1, generally it means that a variable brings additional information to the model. And look, those results are extremely consistent with what you see over here in case of posterior inclusion probabilities. Here we have 2 variables. They're like barely significant. And their PIP is above 0.5. And here we have the variables that are definitely significant. But remember, in case of Bayesian model averaging, we call them robust because it's more than significant. It means that they are significant regardless of the specification of the model. So it means that there should be in the model for sure. Okay, so I think this is it. What you need to... Oh, and here you have posterior probability of a positive sign. I usually do it like... When I make a table, I usually do it like this. Posterior mean, posterior standard deviation, and the probability of positive sign. So look, here what you want to have is either 1 or 0, which means that the coefficient is always positive or it's always negative. And you see over here, the right up till this moment, signs are stable. And here we see that this variable is generally positive in most of the model, but it's negative in some, which testifies to model instability. When you have a situation like this, it's a complete crap, basically, because it's in some models positive, some models negative, because probability of a positive sign is around 50%. Okay, and that is enough. I think you have all the information you need to build your model. You can use all 6 variables. Use your better judgment which one you can use, which one you want to use in the final version of your thesis. And remember, the rest you can just put as robustness checks in appendices of your thesis. Okay, so this is it. Thank you for your attention. Hope this is helpful. Take care.